Hello, folks, and welcome to the third talk in system security. So if you guys remember back a long time, back to the very start of the course, you might recall that we talked about these three main components in security, where the first thing was the security policy. So a specification that says which events do we want to allow in our system, which states do we want a system to be in order to make sure that our security objectives are upheld. And then we have, after this, we have the threat model, which is a specification of which attacks do we want to protect our system against, which attacks are so likely that we think we need to do something about them. And also, of course, which attacks are so unlikely that we will not do something about them. And of course, we want to make sure that these security objectives that we state in our security policy, that we actually meet them, even if we're under these attacks. And to make sure that that happens, we have our security mechanisms, which basically are all the technical solutions that we use in order to make sure that even if we are under these attacks, that the security policy still holds together. This can be cryptography, it can be physical hardware devices, passwords, what have you. Okay, and the main focus in this talk here is the security policy. What is that in more detail, and how do you design one? So in order to connect this to some of the notions we've seen before on the system security, you could say the security policy here is basically the specification that the trusted computing base must follow. So there is some sort of relation there. Basically, the security policy is what the trusted computing base has to refer to in principle, at least. So when some event is about to happen, some user asks for access to something, for instance, the trusted computing base has to take a decision. Do we allow this or don't we? Then we go back to the security policy and figure out, is that something that is allowed here? Of course, it's not always as simple as that, because the security policy will often just be human readable text. And of course, you can't expect a computer-based system like this, the trusted computing base, to go back and interpret humanly readable text. But in principle, there is this relation. Okay, so security policy, first of all, what is that then? Well, we've looked at this a little bit before, but it's basically a three-part thing. So first of all, it is a specification of the system that we are trying to protect here. So the reason why that description or specification of the system should be there is because it's important to limit the problem that we are trying to solve. We cannot solve all security problems in the world. So we better say it's this system or this part of a system that we're making a security policy for, and not whatever else is around. So for instance, as an example, let's suppose we're building a software-only system. And this system, this could be a web server or something else. And let's say that this is hosted on some web hotel. And these guys that run the web hotel, they say, well, we have machines that we run, we're behind a firewall, we have all kinds of intrusion detection systems running. So we're pretty sure that there will not be any attacks that break into our machines. And you could then decide to say, okay, that's then taken care of elsewhere. So the security policy we are dealing with here is only a security policy for that software system we're designing here, and not for the entire computer system on which it will be running. Okay, so important to specify what is it exactly we're protecting here. And then we have, of course, the rules, so the security objectives. What are we trying to achieve? What is allowed? So this is not a very precise definition, of course, but the point here is that what we're saying here is either, in some cases, even in computer readable formal language, we can specify what is allowed, but most often it's actually just in human readable language that we say what is it overall that we want to allow? How is information supposed to flow in the system, for instance? And then we have quite often some kind of high-level strategy for how we get security. So what I mean by this is that we could say something here about how is it that do we use cryptography? Are we having a multi-user system? How do people log in? Is this via one-factor, two-factor authentication, for instance? Sorry about that. So this thing is not always there. Oops, that was the wrong thing. Sorry. Okay, so this strategy here is not something that is always there, but often is. So as you can see, the main part is this business about what are the security objectives, what do we want to allow in our system. So say you're tasked some years up in the future, you might be working for some company and might be tasked with designing one of these things here. So how do you go about this sort of thing? So fortunately, lots of people have thought about these, and tons of security policies have been designed all over the world. And therefore, there are also lots of different templates out there you can follow, or as it's also called, models for security policies. And in order to get into that, I need to first tell you about a mathematical concept, actually, which is a lattice. So that was supposed to be an L, which actually didn't quite work. So let's try again. Okay, so a lattice is a mathematical concept that I'll try to talk about now what it is from a formal point of view, and then we'll talk about later on what this has to do with security policies and their design. But I should say immediately that some of you might have heard about lattice-based cryptography, and that is a totally different kind of lattice. That's not what I'm talking about. So a lattice, in order to talk about this, maybe the best thing is to talk about an example first. So let's say that you have a certain file or part of a system to which you can have certain access rights. And it could be that you have nothing, which I'll denote bot. It could be you're allowed to read the file, maybe you're allowed to write to the file, or maybe you're allowed to do both. Okay. So if you wanted to, so I want to draw a diagram now that sort of shows how these different rights compare to each other. So which right is more than another right. So it's kind of obvious that being able to do nothing is the least you can have. Being able to do both is the most you can have. And it's also clear, of course, that being able to read is more than being able to do nothing. And being able to read and write is more than being able to only read. And similarly for write, there's also this relation there. But notice that being able to read or being able to write, it's not clear that one is sort of more powerful than the other in a sense. So there's no comparison there. So that's what I mean by this diagram here, that whenever there's a line like this guy here, for instance, that means that the guy on the bottom here is less in some sense than the other thing. So this is an example of something called a partially ordered set, where we are able to compare some of the elements, but it's not clear that every pair of elements is comparable. So therefore, let's generalize this a little bit, and let's say that. And let me just copy my little example here, so you can remember what it said. So we have read write, and we have read, we have write, and here we have nothing. Okay, so what I want to define now more generally is a lattice, first of all, is a set, S, let's call it, a finite set, and a relation, which I will denote like this. So I'm just borrowing from the integers this relation that one thing is less than or equal to the other. And so this relation here is defined for not all, but possibly some of the pairs, let's say A and B, which are in where both components in the pair are in S. So when we say that A is less than or equal to B, yeah, what this means is that relation less than or equal is defined for A and B, and we have decided that in this set, in this context, A is less than or equal to B, and this could refer to in concretely in a system that this could relate to or refer to concrete access rights to something, but it could also be different, and we'll see what the possibilities are later on. Anyway, so this relation here must satisfy some basic rules in order for the whole thing to make sense. So the conditions we have are, first of all, that we have something called transitivity. So if A is less than or equal to B and B is less than or equal to A, sorry, that was not. So if B is less than or equal to C, then it must follow that A is less than or equal to C. So notice here, of course, this is something that would be trivial if we had numbers, but this is not what we have. We have just abstract elements in a finite set and this relation here. And of course, it would be possible to define the relation in a stupid way, so that this would not be satisfied, but we assume that this really is always satisfied. Okay, also A must be less than or equal to itself. Kind of makes sense, I guess. And then we have also that if A is less than or equal to B and B is less than or equal to A, it actually follows that A and B are the same element. So these are just kind of, I guess in some sense, sanity checks for such a relation in order to sort of make intuitive sense of the idea that if A is less than or equal to B, then B is more than A in some reasonable sense. But then there's an extra kind of two properties which really are what makes a lattice be a lattice. And what they are, so we have the existence of something called a least upper bound, also known as LUB, of two elements A and B in my set. And this least upper bound of A and B must be another element in that same set S. So let's call it C, just for now. And what this least upper bound must satisfy is the following: that first of all, it's an upper bound, which is kind of, clear that A is less than or equal to C, and also B is less than or equal to C. So C is actually in my ordering of the set. C is above both A and B. It's an upper bound. But also C is the least upper bound, and what that means is that there is no other upper bound which is less than C. Okay, so what I'm saying here is that, more formally, what I'm saying is that for all D with the property that the D is also an upper bound, so D is also above both A and B, then we have that in fact C is the least upper bound, so C is in fact less than D. Okay, so what we're saying here is that in terms of there's only one candidate for being the least upper bound. Maybe it helps to draw an example here. So if I would draw my diagram from before, which was, you have these four elements in my set, and we have these relations where this guy is less than that guy and so on, then if I think about my A and B would be these two elements here, then of course the least upper bound would be C here. And this works because C is above both A and B, and there's nothing sort of between C and A and B. There's no other candidate. So then I could make a different example by changing my diagram here and say, what if I make something like this instead? So now I have A and B, and I have maybe C and D here. So now I have to find myself a new relation. It's now a bigger set. And I have defined that D is greater than A and greater than B, and C is also greater than A and B, but there's no relation between C and D. In this case, something is wrong. I don't satisfy the definition for this particular set S here in this relation, because you can see that C is a candidate for an upper bound for A and B, but so is D. And the definition up here says that if I find such a D, it must be above C, because C is supposed to be the least upper bound, and this is simply not the case here. So this one doesn't work, but this one over here is fine. Okay. I should also say that you have to remember that it says this least upper bound here must be defined for all choices of A and B. Particular means must also be defined even if A is equal to B. So that also must be the case. So this would mean, for instance, that if I had something like this here, and then it forks up here, this would also not be allowed, because this element here, I could choose this element to be both A and B in my definition, and then these two guys here would both be upper bounds, but there's no relation between these two guys, so this is not going to work. Okay, so that's the least upper bound. And then there is also something called the greatest lower bound. And you can probably maybe guess, so the DLB of A and B, again, is a new element which must also be in my set S. And you can probably imagine that this is simply, you take everything I said about the least upper bound, you stand on your head, and then you say exactly the same thing. So what we're saying here is that in our diagram from before here, if this was A, if this was B, then the greatest lower bound for A and B will be this element down here. And just like before, this must be the only candidate that there is, so to speak. So again, if my diagram was different, so I had this instead, then the definition of greatest lower bound would no longer be satisfied. Okay, so what this is basically a mathematical concept called a lattice, and I've given you the definition here, and this is just an abstract mathematical definition. And then what we do now is we go and we start talking about what can we use these lattices for. So the point is that a lattice is a concept we can define, and we can use this when we want to specify, for instance, how in our security policy we want to allow information to flow in our system. So I need a few concepts for this. So first of all, I want to define objects and subjects in my system. So subjects in my system will be those actors that do stuff, that take actions on their own account. So this will be users, for instance. It can also be processes or software processes that run. So those will typically be entities that go to the system and ask for access to something, for instance. Whereas objects are, well, as the word says, these are things that do not by themselves take any action. So objects will be files, for instance, and maybe other resources in my system. So basically things that don't take any initiative by themselves, they just sit there, and whenever they ask to do something, they will respond. So I can write to a file, I can read from a file, I can send stuff to the printer and get stuff out. These would be typically be objects. So then what I can now start thinking about is to think about what in a situation where some subject S, so S will be one of these subjects here, O will be an object, and now S asks to do some operation up here on an object O. So I want to read from this file or whatever. And should this be allowed? So, so in other words, that's what the trusted computing base will have to think about when it gets this request. Should I allow this or not? And now the point is that a lattice, the concept of a lattice, gives you a systematic way of setting up, doing a setup where you can answer this question in a reasonably compact way, as we'll see. So in order for this to be the case, I need a lattice. It can in principle be any lattice you like. So any set large S plus this relation here, and this has to follow all these rules that we talked about before. And then we need a classification. So a classification is basically a function. It's function C, and it goes both from the set of all subjects. That was not subject. Let me try again. So it goes from all subjects into my lattice S, and it also defines a function from the objects into my lattice here. And what this means is that then when I have this request, so that involves the subject S and the object O, then I can talk about the classification of the subject S. I can talk about the classification of the object O that he wants to do something on. And then because I have now mapped myself into the lattice, I can ask, for instance, is the classification of the subject less than or equal or greater than or equal to the classification of the object, or maybe there is no comparison between the two in my lattice. But the point is that then, based on the result of this comparison here, I can take a decision on whether I want to allow this operation or not. So, for instance, what you could say would be something like, if I will only allow subjects to read from this object there if the classification of the subject is at least as large as the classification of the object, for instance. And you can design any kinds of rules like this, where the rules, of course, might be different depending on which operation you want to execute, and so on. So this is a very general way of designing a security policy, because the lattice can basically have any structure that you like it to have, except of course they have to satisfy the definition. Let me give you a very simple example of a security policy that follows this principle here. It was in fact the first security policy anyone ever defined formally, and this was done by Bell and LaPadula. These two guys worked for the American Army back in the 60s, and those were the days where, whenever you had a computer, it would be one big mainframe computer that everybody would have to use. And of course, it was worried that if everybody using the same computer, the same hard disk and everything, then everybody can see each other's files, and something had to be done about this. In particular, of course, in a military context where you're dealing with secret data, and you want to make sure about who can read what and how information flows. So what they did was that they defined, what was actually a very simple lattice. Not that they knew about the concept of lattice, but that was what they defined. So they looked at something like this. So different levels that are directly above each other. This is a very simple example of a lattice, of course. So you could name these things, for instance, public and secret, and maybe top secret up here. And so the idea was that what they said was we're going to define classification. So every subject here gets mapped to one of these levels here, and also every object gets mapped to one of these 3 levels. That's the classification I was talking about before. And so what they were worried about was basically confidentiality. How do we make sure that information that's top secret, that's classified as top secret, will not flow down to the more public levels? And what they said was, well, we can actually do this by having 2 rules. And basically, if what they said was, if it's pretty natural, if subject S wants to read from an object O, then this is okay, but only if the classification of the subject is at least as large as the classification of the object. So what that means is that if you are top secret, you can read from levels secret and public. If you're secret, you can read from levels public and from your own level, of course. But a guy down here in the public level cannot read from the upper levels, which makes sense, of course. And then there was another rule. If S wants to write to object O, then they say that's okay, but only if the opposite inequality is satisfied. So only if the classification, of the subject is less than the classification of the object. So the idea here is that you do not want someone who is on top secret level to write to the lower levels here, because that might mean that he's revealing data to a lower security level that he shouldn't be revealing. But it's okay that a guy on the public level here writes files that are top secret, because that doesn't reveal any information that should not be revealed. So with these 2 rules, I'm sorry, that was not supposed to happen. So I said this is okay if the classification of the subject is less than or equal to the classification of the object. Okay, so what this does in this example here, what this does is that it makes sure that information always flows upwards in the system. So this might not seem like rocket science to us today, but it was in fact a major achievement, because it was the first security policy anyone ever defined and actually implemented in real life. So you can easily imagine that this diagram here, which is very simple, could easily be generalized to any lattice, and you could have similar rules. There is also a different model known as the Biba model. So this is also a guy with that name. I guess for some reason security policy guys have strange surnames, but that's something we have to live with, I guess. So the thing is that what Biba did was he did something very similar, but where Biba Model actually had dealt foremost with confidentiality. So about keeping things secret. What Biba was talking about was authenticity. So if you are worried about your data system being authentic, how should information flow? So the idea would be that he also talked about some levels directly on top of each other. But this time, the idea is that what is on top is the most reliable information. And here, down here, we will have least reliable. One example that you might think about here is, what if you have a system where that runs a train system, for instance. So in the most reliable department up here, you will have the part of the system that knows where every train is and makes sure that the changes of tracks and stuff is done in such a way that trains don't run into each other. So they will need information to be reliable about where are the trains. Down here, you might have a publicly accessible part of the system where you have the screens that are shown on the train stations that will show whether you have delays and stuff like this. So the principle that he said was then we can do something reasonable here in the authenticity case by simply taking the rules from Bell and Lapadula and just turning them on their head, so to speak. So he said, well, the subject can read from object O if it is the case that the classification of the subject is less than the classification of the object. Now, so the idea here is that if I'm on the least reliable level here, I'm allowed to read from the more reliable level. So that makes sense. The system that will show train times on screens and stations is allowed to read from the part of the system that actually knows where the trains are. On the other hand, when are you allowed to write to an object O? Well, this is okay. We can say if the classification of the subject is more than the classification of the object. So the idea is that if I'm a subject that have access to really reliable information, I can write down. But if I'm on the least reliable level here, I'm not allowed to write information upwards in the system here, because that would mean that maybe I contaminate the more reliable part of the system by less reliable data. So there are these two ways of using a lattice, a very simple lattice, but of course the structure of such lattices can be in principle infinitely complicated. So let me just end this part in lattice-based security policy by just mentioning that, motivating why I've been tormenting you with this mathematical definition of lattices, why all these conditions and least upper bound and greatest lower bound and so on. So the idea is the following, that if you have such a lattice-based security policy, there are various natural questions you want to ask yourself also while the system is running. Like, for instance, the following question: who can read from, say, both object O1 and object O2? So let's say two different files. And which users, which subjects will be able to read from both these guys? And if we organize things with a lattice, there is a very simple and compact answer to this question. Namely, the answer will be, it will be any subject S whose classification is at least the least upper bound of the classifications of the object. Okay, so we take the classification of O1, we take the classification of O2, and we look at the least upper bound on this thing. So and this again, this least upper bound again, I remind you, is an element in our lattice. So this is an existing classification. So this means if we want to see, can I do both these things? We just look at this one part of the lattice. If I had not demanded that my system be based on a lattice, then this answer, this question here, could have an infinitely long list of classifications as answers. So if I would allow, weird things like there would be a diagram of this form here, that forks out in this way, then it would get really heavy to handle, and we don't like this. So that's why we insist that things be a lattice. Okay. So I just want to mention now that although a very large number of templates can be derived from this lattice-based approach, a lot of templates for security policies can be derived from a lattice-based approach. There are also other approaches, and I'll leave those things for you to read for yourself. I can mention there are things called the Chinese wall title policy. There's prevent, detect, recover. There's a whole bunch of other things, and those are really straightforward. And I think they're actually best studied by yourself. So that is therefore the end of the talk on security policies. The next and final talk on system security will be on access control.